Welcome students in the series of wave optics. Today we will take in the topic laws of reflection of a plane wave using Huygens principle. This topic is important for the CBSE, NEET as well as for the IIT JEE aspirants. Let's move with the first topic, laws of reflection. So, from the earlier knowledge, like from the Newton's corpuscles theory or Newton's corpuscular theory, we know that light is a form of particles which consists some momentum. And Huygens want to replace this theory by wave nature. So now we are going to prove this law of reflection by the wave theory. Earlier we was prove this complete theorem by the help of particle or a corpuscles theory. So from the earlier knowledge, we know that angle of incidence is equals to the angle of reflection. That means angle I is equals to angle R. This is the case when we are taking the light as in particle nature. The second law is the incident ray, reflected ray are normal to the reflecting surface at a point of incidence all lie in a same plane. Again, these two laws comes out when we are taking the light as in particle nature. Incident and reflected ray lie on the opposite side of the normal. So now let's first observe the phenomena of reflection by using plane wavefront. So phenomena of reflection. We are taking a surface which is again completely smooth. We can take the surface as a mirror also. So this is the wavefront AB. And as you can see, this is moving from one point to another point. This is the motion of a wave. At this particular point, as you students observe, it's not equal wavefronts. They make an angle some theta over there. So A prime, B prime or A prime P is a particular point at time t. The distance which we cover by reaching this point, the same distance it will be reaching at the surface point. We are taking these points as an R, B prime. It makes some angle. So A prime R is equals to P B prime, which is equals to C into T. Because distance is equals to speed into time, from that we can say the scenario. If we just drop a perpendicular in the both the surface, so we can say that a new wavefront is a form over there, which reflect back from this and making perpendicular with this both the wavefront. So waves are moving and that waves are perpendicular to the wavefronts also. So here A double prime and B double prime is the location of that reflected rays actually. Minimum condition to get this value. This is the incident angle. So here we observe the angle I is the incident angle, which makes actually A prime B prime in a halfway. So when A reaches XY point, A prime B reaches point P and it over to additional distance PB prime to reach XY. During this time, the ray at A prime is already reflected from XY and reaches the point R. Since the medium remains same, so the velocity of the wave we can say remains same. Thus, it converges equal distance in a same interval of a time, which is if I'm taking a small t. So, A prime R is equals to PB prime is equals to CT. This implies that distance covered from A prime R is equals to distance covered by P B prime. So A prime R is equals to PB prime. Now since the wavefront is perpendicular to the wave normal, then angle R should be equals to 90 degree. So we join the point B prime up to point R to get a plane wavefront. Now here, as you can see students, I think you observe this is the angle R, which we are saying as the angle of reflection. This is a reflected wave, friends, and this is a reflected waves. Minimum condition to get the value of R, that R should be less than 90. A prime R is equals to PB prime. Consider a wavefront AB, which is falling on the surface. Here A prime, and B prime are the incident ray. Now using PB prime is equals to A prime R, draw semicircle using point A. For angle R is equals to 90 degree, draw the tangent on the semicircle. Which is showing the value of a reflected ray. And this comes from Snell's law. So let's begin with the proof of Snell's law. So from triangle A prime R B prime and triangle A prime B prime, A prime B prime is equals to B prime A prime, which is in a common side. B prime is equals to RA prime, which is equals to constructions. Triangle A prime RB prime is equals to triangle angle A prime PB prime, which is equals to 90 degree. That means wavefront is perpendicular to the wave norm. In triangle A prime RB prime is similar to the triangle B prime PA prime from these observations. So we can say angle RA prime B prime is equals to angle P B prime A prime. So the value of R A prime B prime is 180 minus R, which is equals to 180 minus I. So from this we can say angle I is equals to angle R. This is a simple proof of the wavefront to say that angle I is equals to angle R concept. This proves the law of reflection. So here the Huygens actually succeed and they prove the law of reflection by their wavefront form. Now second, as you can see students, the incident ray, reflected ray, and the normal to the reflecting surface. At the point of incident, all lie in a same plane, and incident and reflected rays lie on the opposite side of the normal. Now let's take some multiple choice questions for more clearance the topics. In the same medium, light travels with a different speed, constant speed, minimum speed, or a maximum speed. The medium is same here. So students, the correct answer is constant speed. Second, incident and reflected ray lie on dash side of the normal. Same, both, opposite, not defined. The correct answer for this question is opposite. According to the law of reflection, the relation between the incident angle I and the reflected angle R is given as angle I is not equals to angle R, I is greater than R, I is less than R, and I is equals to R. So the correct answer for this question is I is equals to R. Plane wavefront on the reflection gives spherical wavefront, cylindrical wavefront, plane wavefront, none of normal. The correct answer for this question is a plane wavefront. Now, reflection topic we already proved. We are now moving on the law of refraction of plane waves by using Huygens principle. So, law of refraction. From the previous knowledge, as I told you, from the particle nature of a light, or we can say Newton's corpuscular theory of a light, we have a law of refraction also, in which for a given medium, the ratio of a sine of angle of incidence to the sine of angle of refraction is given by in this form. As you can see in this diagram below, angle of incidence I is strike on the point on incidence and because of the medium changement it will be deviate from its own path. So the light rays wants to go in this form because of the changement in the media it will be bent towards the normal. Where the bending occurs, students? Towards the normal. Now n is equals to sine I by sine r. This is the Snell's law. So what is the physical significance of this? So the medium's property when the light travels or the light basically how the light behaves in the changement in the medium that will actually tell refraction. Second law, incident ray, refracted ray and normal to the surface at a point of incidence all lie in a same plane. Incident and refracted ray of light lie on the opposite side to the normals. This is a rare medium, this is a denser medium. So, this is a wavefront which is incident or strikes on the rare surfaces or the interface. We are saying this medium relation we are saying as an interface. Here the wavefront actually moving. So as you can students see, when this point wavefront strike on this till here, it takes some time or it covers some distance which is in the form of a CT. And when the light ray reaches here, then that second point reaches at the surface. So V1 is equals to speed of light in a rare medium. V2 is equals to speed of light in a denser medium. And when the light rays is striking from the rare medium to the denser medium, it will be bent towards the normal, as you can see over here. So consider a plane wavefront which of a monochromatic light rays, light A prime, B prime obliquely incident at the refracting surfaces. When the wavefront reaches at point A, it becomes secondary waves in the second medium. So students, as you can see over here, like whenever we are taking the nature of a light in the form of a wave, we are seeing like many changement occurs in the phenomena. Like in the case of plane wavefront, we must take a monochromatic light rays. There will be few new phenomena which is observed that we can't prove by the help of wave theory. It becomes secondary waves. So A prime B prime is equals to AB, which is the incident wavefront. And when A prime reaches at point A, B reaches at point B, and B needed extra time t to reach xy plane. Since speed of light in a rare medium is greater than speed of light in a denser medium, for same time t, distance traveled in a rare medium is greater than distance traveled in the denser medium. So V1t is greater than V2t. Consider V2t is less than V1t with A as a center drawn from the hemisphere of radius V2t. And during this time, secondary wavelet at a cover of a distant V2 in a denser medium. Draw tangent CD to the secondary wavefront, and CD is a refracted wavefront. Now here, angle A prime AN is equals to I, angle C AM is equals to R, NAM normal to the XY ray. V1 is equals to speed of a light in a rare medium. V2 is equals to speed of a light in a denser medium. So from figure, angle A prime AN plus angle N prime AN is equals to 90 degree. So triangle ANAB plus triangle BAD is equals to 90 degree. So we can say triangle A prime AN is equals to triangle BAD, which is equals to I, triangle MAC plus angle DAC, which is equals to 90 degree. Triangle DAC plus triangle ADC is equals to 90 degree. So we can say that angle MAC is equals to angle ADC is equals to R. If I'm just taking the triangle BAD and triangle ACD, the sin I is equals to BD by AD and sin R is equals to AC by AD. Sin I by sin R is equals to BD by AD and AC by AD, which gives the value BD by AC, which is equals to V1T by V2T. Now, sin I by sin R is equals to V1 by V2. Also, refractive index 1 mu 2 is equals to 1 mu 2. Mu 2 by mu 1 is equals to V1 by V2. This comes from the Snell's law, where refractive index actually that constant which tells that the nature of a light in a different medias. Students, as you know here, like this is a given already. 1 mu 2. That is a refractive index of a second medium with respect to the first one. This is a line states that sin I by sin R is equals to constant, and that constant tells the nature of a refractive index And refractive index tells the nature of a light in a different medium. Means of like as we know, during the medium changement, frequency remains constant. So all these things are comes by the help of refractive index. Now Snell's law, we have to know that this law of refraction can deduce from the Huygens theory also. So as we know that Huygens theory have some productive things like this is angle I, this is angle R, and the first rule which we know that sin I by sin R is equals to constant, that is called as a refractive index, and the second one is incident ray, refracted ray, and the normal to surface at that point of incident, all these lie in a same point. So as you can see over here also, I, R, all these lie in this interface. This interface is not actually changing. So incident and refracted rays lies on opposite side of the normal. Now let's take some multiple choice questions so that we can understand like whatever we understood is a complete or not. So according to the Snell's law, we have an option I plus R is equals to 0, I is equals to R, sin I is equals to sin R, sin I by sin R is equals to constant. So this is the correct answer. According to the Snell's law, we know that whenever light rays passing from one medium to another medium, this will be change. And the changement tells by a constant which is called as a refractive index. I hope students you understand. Next, if C1 and C2 are the velocities of a light in a rare and denser medium, then C1 is a greater than C2 by 2, C1 is a less than C2, and C1 is equals to C2, and C1 is a greater than C2. So students, as we know, the rare medium is a medium where the medium particles are far away from each other. Whereas if I'm just taking a denser medium, so the medium particle are a rare, like very close to each other. For that, like light ray have to do some, like lost some energies because of that velocity reduced. So we can say C1 is greater than C2, means velocity of the light is greater than in the rare medium and to comparison with the denser medium. Next question. During the refraction of a plane wavefront, the width of the wavefront is changes, remains same, sometimes changes, and then of these. The correct answer for this question is changes. During the refraction plane wavefront, the width of the wavefront changes. So students, I hope you understand these topics. If there is any kind of questions which is running in your brain, running in your mind, you can ask in the chat session. Till that, take care everyone, and thank you for watching this video.